Hello, you're welcome to our physics class. And in physics today, we shall be looking at the topic current electricity. We make use of electricity in our daily life, especially in powering our appliances. And in this topic, there are three basic quantities which needs to be understood clearly before we will proceed into the calculation aspects. The first one is electrical current. Current is represented as I. The second one is potential difference, which is represented as V. And lastly is electrical resistance, which is represented as R. Let's take the first one, electrical current. Electrical current is the rate of flow of charge around a circuit. Current is the quantity of the charge over the time taken for the charge to flow around the circuit. Quantity of charge has a unit of coulomb, which is represented as C, while time has an SI unit of S. I equal to Q over T. The SI unit of current is ampere. It's represented as A. That's the SI unit of current. We detect current in a circuit by the use of a galvanometer. What does it do? It detects. It is not what measures. And for you to measure it, we need an ammeter for measuring the current that is flowing through a circuit. And you should take note that the ammeter is always connected in series with the circuit. The ammeter is connected into it so that it can take the quantity of current that is passing through this circuit. We look at the potential difference. If you have a circuit and you have to take the potential difference 2 points in a circuit, you are looking for the amount of work done when one coulomb of charge is being moved from one point to the other. So if you have a coulomb of charge which is being moved from one point to the other, and if you decide to look for the potential difference across these 2 points, let's call this point A and point B, you connect an equipment there. That equipment will be able to calculate the potential difference, that is the work done to move that charge from point A to point B. Potential difference is measured with a voltmeter, so we can have it as V over here. The SI unit of potential difference is volts. When current flows, it does so because there is a kind of electrical pressure difference between 2 points in an electrical circuit. And now there's something that is very close to potential difference, which is called the electromotive force. That is EMF, electromotive force. There's a difference between electromotive force and potential difference. So let's say that here we have a key. A key is a switch that turns on and off this particular circuit. And over here we have a cell. And across this place we have a resistor. Here is a cell. Current moves and flows on like this. We want to differentiate EMF from potential difference. When this key is closed, that is in this form, the current will be flowing from one point to the other. So potential difference is the work done when one coulomb of charge is being moved from one point to the other in a closed circuit. But let us say that this circuit is opened, and when it's opened, meaning that there is no current that is flowing in it. When we measure the potential difference between these 2 points, what we are going to get is the EMF. The EMF is the potential difference between the two terminals of a cell when it is not delivering current to the circuit. So when you measure the potential difference here, what you will get is the electromotive force. And in most cases, the electromotive force is greater than the terminal potential difference. Now, another thing you should notice is that a voltmeter is connected across the 2 points because it has a high resistance to the flow of current. This material in which a voltmeter is built with has a very high resistance to the flow of current. And so that is why it is not built in series with the circuit, rather it is built across it. We look at the electrical resistance. The word resistance means disallow or flow of something. In electrical resistance, a substance has an ability to resist the flow of electricity. Resistance is measured in ohms and it is represented as this. Resistance is also known as the ratio of potential difference, which is V, across the conductor to the current flowing through it, which is I. Resistance is the ratio of the potential difference across the conductor to the current flowing through it, which is R equal to VI. And this particular equation is going to be very, very important in solving our questions under electricity. And with this, a graph can be plotted in which we plot voltage against current, where V is in volts and current is in ampere. And when we plot this graph, you have a straight line positive graph. Considering that when we draw a slope, its slope, we'll have it that, let's call this point A, point B, and point C. With this, we'll have a slope which will give us the resistance. Still on resistance. So resistance of a substance is its ability to resist the flow of electricity. Substances that are very, very good conductors are poor resistors, while poor conductors are good resistors. The best conductor that we know is silver, followed by copper. And if you are looking for highly resistant wires, we'll be talking about constantine, manganese. These are very, very good resistors. They can resist flow of current very well. We could have resistors that are connected in series into an electrical circuit. In this case, we have just one resistor here. But imagine if we have two resistors like this. One thing is that the current will flow through the resistor. When they are connected in series, it is the same current that will pass through this first resistor and the second resistor. Just that the potential difference across them will be different. This black here is the potential difference which is drawn across this resistor. Now, if we are to calculate the potential difference across this, it will be different from each other. Now, when these resistors are connected in parallel, just as this, so imagine that we replace this single one with this double. When they are connected in parallel, we have different currents that will pass through each resistor. The current is going to be shared based on the resistances of the resistor, but in this place the same current will pass through it, but different voltage or potential difference. Now, another thing is that when you have resistors connected like this, we call this a series connection. Now, in this series connection, you can get total resistance by adding R1 plus R2. And for this parallel, you can get the total resistance by having 1 over RT equal to 1 over R1 plus 1 over R2. Looking at this particular circuit over here, we've brought in something different. Now we have a cell. Take note that several cells make up a battery. Now, in a cell, the electrolytes in the cell also poses some resistance to the flow of current. And so we have a small R over here. And this is the cell. In the cell, we have the electromotive force from here. Here we have the ammeter, and here we have the voltmeter. And don't forget that we said that we can get the terminal potential difference of a cell. And the terminal potential difference is just like the potential difference between these 2 points when this key is closed. So the potential difference across any point is the terminal potential difference. But when we open this key, current will not be flowing through this circuit any longer. You can calculate the potential difference across this cell. When it is not delivering current, what you are going to get is called the electromotive force. We said that the EMF will be bigger than the potential difference. Why? Because this is the only resistance, or the only resistor that we have in this. But when you consider that the current had to flow through this wire, the wire is going to pose some resistance to the flow of current. Likewise, this resistor. Because of that, the flow of charge will yield a lower potential difference. What is worthy of note is the fact that you could have several cells to make up battery. Now, if these cells are connected in series, just as you're seeing here, the effective electromotive force, so we have electromotive force here, is gotten by saying that, so the effective electromotive force here, by multiplying it by, that is by having the number of cells multiplied by each of the electromotive force, while the effective resistance. Now this resistor here is the internal R. So the internal resistance can be gotten by also multiplying the number of internal resistors by the R itself. Now over here, we could have the cells arranged in parallel. Now when they are arranged in parallel over here, the effective electromotive force is just to take one of the electromotive forces that we have. So we could have 10 volts here, 10 volts here. So it's just by taking just one of the electromotive force. While the internal resistance is gotten by having R over N. That is, take one of the R and divide it by the number of internal resistors that you have. Resistivity and conductivity. Resistivity is represented as this and conductivity is represented as this. Now, the resistance of a material such as a wire is directly proportional to the length of this particular wire and inversely proportional to the cross-sectional area of the material. When this proportionality sign is replaced with equal to, we have our resistivity coming into play. And so here comes another formula which we are going to make use of, which is that resistance equal to resistivity multiplied by the length of the wire over the cross-sectional of the wire. Or it could be written as resistivity is equal to Ra over L, where A we said is the cross-sectional area, which is pi r squared. Now pi r squared could be written as pi, where r equal to d over 2. So we have it as d over 2 all squared, and so that will be pi d squared over 4. Alright, so that is A. Now when you substitute this pi d squared over 4 into this equation, you have resistance is equal to 4 rho L over pi d squared. Talking about conductivity, conductivity is equal to inverse of resistivity. Then another thing we need to talk about is the meter bridge. Now the meter bridge is a device for measuring resistance of a material, and a form of meter bridge is the Wheatstone bridge. It is used for measuring it. And another one we have is the potentiometer. The potentiometer helps to give very accurate measurement of resistance. So we shall look at some questions. So some questions under current electricity. A conductor has a resistance of 2 ohms. If a current of 5 ampere is flowing through it, what is the potential difference across the terminals of the conductor? So we're told that we have a resistance of 2 ohms and that the current which is flowing through the circuit is 5 ampere. We have to calculate the potential difference. There are formulas that we need to take note of, which is V equal to IR, right? And that's what we are looking for. So V, our current is 5 multiplied by the resistance, which is 2. So the answer is 10 volts. A cell of EMF 6 volts and internal resistance of 0.5 ohms is connected across a resistor with resistance 2.5 ohms. What is the current flowing in the circuit? So first is try to get a sketch of the circuit. We have it like this. We're told that now this is the cell, and in the cell it has 6 volts as the EMF and 0.5 ohms as the internal resistance. It has an external resistance of 2.5 ohms. We're asked to calculate the current flowing in the circuit. In this circuit, we should take note that this is the EMF, and we have that current equal to voltage over resistance. Now we will get the voltage if we find it across this place, but in this case we're not giving the voltage, rather we're giving the EMF, and we have that EMF over the external resistance plus the internal resistance, which is R, will give us our current. And so we have it that I equal to 6 over R, which is the external resistance, 2.5 plus the small r, which is the internal resistance, that's 0.5. So we have 6 over 3, and that gives us 2 ampere. So this is the current which is flowing across the circuit. But take note that this EMF 6 volts here is different from the potential difference across these points. Calculate A, the current in each external resistor. B, the potential difference across AB in the diagram. So here is a sketch of the diagram where this is the cell, this is the EMF, and here is the internal resistor. We have an external resistor which is 1 ohm, and we have these two other external resistors which are in parallel. We were asked to calculate the current in each external resistor. So we find the current flowing here, and current flowing here. So let's take it like this. First, let us calculate the total resistance of these parallel resistors. So we have it that the total resistance will be 1 over total resistance equal to 1 over 10 plus 1 over 5 for the parallel. So here we have 10, 1 plus 2, 1 over RT, so that will be 3 over 10. So 1 over RT is 3 over 10. So what exactly is RT? We can get our RT by multiplying this 3 with this RT, which is 3 RT equal to, then 10 multiplies 1. So we are left with RT to be what? 10 over 3. So we have an RT of 3.33 ohms. That is the total resistance for these two resistors. Next, it is in series with 1 ohm and also in series with this internal resistor over here. We want to calculate the whole resistance. So we have it that since they are in series, we have the 1 ohm, which is this, plus this one, which is 10 over 3, plus this 2 over 3. So we have 3 plus 10 plus 2, and that gives 15 over 3. So we are having 5 ohms as the total resistance in this circuit. Now after that has been gotten, we will now calculate the current which is flowing in this circuit. And we calculate the current by saying that current is equal to E over all this R, all the R, which is the RT. So the electromotive force here is 3, and the total resistance is 5 ohms. So 0.6 ampere. So this is the current that is flowing through the entire circuit. With that already gotten, that current is the exact current that is flowing through this 1 ohm. We have gotten the first one, that's the first external resistor. Current through the 1 ohm is equal to 0.6 ampere. Alright? They want to calculate the current through this. Now, we said initially that when the current comes here, it separates depending on the value of the resistor. What we need to do at this stage is to know the potential difference across these 2 points. So what we need to do first is to know the potential difference across these 2 points, because the potential difference across these 2 points is the same thing for the two of them. So how do we get that? We know the current flowing through it, which is 0.6 ampere for the first one, and then for the two of them, that's for these two parallel resistors, we have a total resistance of this, that's 10 over 3. So we have that we are going to use, 10 over 3. So to get the potential difference, which is V, is equal to 0.6 times 10 over 3, and that is 2 volts. It is 2 volts that is the potential difference. Now we're going to use that potential difference with this 10 ohms to calculate the current that is flowing through this place. So we will now say that for the 10 ohms resistor, the current flowing through it will be the voltage over R. The voltage is 2 volts over 10, and that will be 0.2 ampere. Then, talking about for this second one now, for the 5 ohm resistor, the current that will be flowing through it will be the potential difference, which is 2 over the resistance, which is 5, and that will be 0.4 ampere. From here, we have calculated the current flowing through the 1 ohm, 10 ohms, and the 5 ohms. Next, the B part says we should find the potential difference across AB. That will mount a voltmeter across this place and look for the potential difference. The current flowing through the circuit still remains 0.6 ampere from our earlier calculation. Then the resistance is 1 ohm. So the potential difference across this place will be I times R, and that is 0, and that will be 0.6 multiplied by 1, and that's 0.6 volts. That is the potential difference across this point. It says a battery of 15 volts and internal resistance 5 ohms is connected to a resistor of 20 ohms. Calculate the terminal potential difference. Here is a sketch. We are told that the battery is 15 volts and has an internal resistance of 5 ohms connected to a resistor of 20 ohms. We have to calculate the terminal potential difference. So we could calculate the potential difference across this point, especially when it is opened. We should take note that the current flowing through the circuit is equal to the potential difference over R, which is also equal to the electromotive force over the external resistance and the internal resistance. Yes, we're not given a current, but in this question, we're given the EMF to be 15. That is the voltage of the cell. We are looking for V. We have our R. Now this R here is for this external resistor, which is 20, and the EMF, which is 15 over R plus R, that is 20 plus 5. So we have V over 20 equal to 15 over 25. So V equal to 20 times 15 over 25. And when we multiply this, we would have 12 volts. What length of resistance wire? 14 ohms of diameter 0.3 mm and resistivity 1.1 times 10 to the power minus 6 ohms meter resistor are we going to have? So in this question, we state our parameters. We're told that the resistor is 14 ohms. We have a diameter of 0.3 mm. We have a resistivity of 1.1 times 10 raised to the power minus 6 ohms meter. So this is the SI unit of resistivity. It's advisable that we convert this 0.3 mm into meter. We'll divide by 1000. When we divide by 1000, we have 3 times 10 raised to the power minus 4 meter. Then we bring in our formula, which says that resistance is equal to 4 rho L over pi d squared. In the question, we have to look for the length, which is unknown. So make L the subject of this formula. When we make L the subject of the formula, you would have L equal to R pi d squared over 4 rho. So let's substitute our values into that formula. We have 14, pi is 22 over 7 times d. Our diameter over here is 3 times 10 raised to the power minus 4 all squared divided by 4 times rho, which is 1.1 times 10 raised to the power minus 6, alright, times the resistivity. So we could solve this gradually by having 2 over here. So we have 2 times 22 multiplied by, this means 3 squared, that is 9. Then 10 minus 4, then 2. That will be 10 minus 8 over, we have 4 multiplied by 1.1 times 10 to the power minus 6. 2 here 1, 2 here 2, then this gives us 11. Alright, we could move this decimal here and we'll have 0 here. So we have 11 times 90 times 10 to the power minus 8 over, this now is 11. Now this 10 to the power minus 6, let it move up. When it moves up, it becomes minus 6. And that means we have plus, right? So minus and minus turns to plus. So 11 cancels 11. We have 90 multiplied by 10 to the power of minus 8 plus 6. And that gives us minus 2. So when we multiply this out, this will be 90 times 1 over 100, and that is 0.9 meter. So the length is 0.9 meter, or change it into millimeter. So the answer is 0.9 meter. Here comes the next question. It says, in the meter bridge shown, calculate the resistance of R. What will be the balance point if R is changed to 30 ohms? So here we have a 2-in-1 question. Here is a sketch of the diagram. Now in this meter bridge, this point is being adjusted, and when it is adjusted, it will give different resistance at the resistor. So here is how this question is solved. In the first instance, we were told to calculate R. Now from here to here is always 100, except stated otherwise. So if from here to here is 100, it means that this remaining part will be 100 minus 60. So we'll solve this question in form of a ratio, where we'll say R over 10, that's the resistance here over the resistance here, is equal to this length over 100 minus 60. R over 10 equal to 60 over 40. Making R stand alone, that would give 60 times 10 over 40. And so we'll have our R to be what? 15 ohms. So this is what the resistance will be. But we're told that if R is 30, now we're giving R now to be 30, what will be the new balance point? So we need to adjust, this is a wire that we need to adjust. Now what will be the new balance point? So in that case, we'll have this place as 30 now. 30 over, this still remains as 10, equal to, let's say that this is place we are adjusting. We don't know what the length here is going to be. If this place is x, that means the other side will be 100 minus x. So we have our x here, then we have 100 minus x. We cross multiply and we have 10x equal to 30 into bracket 100 minus x. So we have 10x equal to 3000 minus 30x. We collect like them, so we have 10x plus 30x equal to 3000. Here is 40x equal to 3000. So x equal to 3000 over 40. We'll be left with 75 centimeters. So meaning that this wire here will move towards this place. So if it moves towards this place, that means if this place is 75, this place, the remaining place will be what? 25. That's 100 minus 75. Here comes the next question. It says that if the potential difference between X and Y in the circuit is 10 volts, what is the current flowing in the circuit? So we have our X and Y. We are told that the potential difference across this point is 10 volts. What is the current flowing in the circuit? Alright, so we have several resistors that are arranged in parallel. So we'll take this place first and determine its total resistance. How would that be gotten? So we have the total resistance for this first box is 1 over 3 plus 1 over 3 plus 1 over 3. And that would give 3 over 3, and that is 1. So RT over here is 1. Likewise, in this other box, the total resistance is also 1 over 2 plus 1 over 2. So that's 2 over 2, and that will be 1. So the RT for the other one too is 1. So we'll have that our total resistance will be equal to 1 plus 1, and that is what? 2 ohms. So all these are 2 ohms. We're told that the potential difference across this point is 10 volts. We have to calculate the current flowing through it. Now the current flowing through this is voltage over resistance. Voltage is 10 and the resistance is 2. So we are left with 5 ampere as the current. Alright, so let's move on to the next question. It says two resistors of resistance R and 5 ohms are connected in series to a battery of EMF 24 volts and internal resistance 1 ohm. If the current through the circuit is 3 ampere, find the value of R. So we'll make a sketch of the circuit. We have So we have R, and we have 5 ohms resistor, and then we have 24 volts over here and 1 ohm over here. We have a current of 3 ampere flowing through the circuit. For us to solve this, we should realize that current is equal to voltage over resistance. That is, if you have a potential difference across the 2 points here, that will give you your potential difference over the total resistance. And that's also equal to the EMF over R plus R. So what we'll do is, we're given the current, we're given E, we can get our R, which is the external resistance, and then we have the internal resistance. So we're going to make use of this with this. Alright, so we have our current as 3 ampere, electromotive force as 24 over R plus R. Now let us represent all this. At first, let's represent it with P, So when we have it as P, so we take it as P equal to 24 over 3, and that is what? 8. So we have 8 ohms as what the total will be. So in this case, since the resistors are in series, all we need to do is to add R plus 5 plus the internal resistance, which is 1, equal to the total, which is 8. So we have R plus 6 equal to 8. So R equal to 8 minus 6, that gives us 2. So 2 ohms is the value of R. The next question, which says a battery of 3 cells in series, each of electromotive force 2 and internal resistance 0.5 ohms, is connected to a 2 ohm resistor in series with a parallel combination of 2 3 ohm resistors. Draw the circuit diagram and calculate A, the effective external resistance, B, the current in the circuit, C, the lost volts in the battery, D, the current in one of the 3 ohm resistor. Alright, so first thing is to draw the circuit, and here it is. We have 3 cells. We have this as the first cell, this is the second cell, and the third cell. And so this makes a battery which is connected into the circuit. We have the 2 ohm resistor which is in series with 2 parallel resistors. Then A says that we should calculate the effective external resistance. So to calculate the external resistance, we just want to consider this resistance up here. So first, let's know what the total of the parallel will be. So we have 1 over RT, that's the total resistance in this parallel one, equal to 1 over 3 plus 1 over 3. So we have 2 over 3. Hence, RT equal to 3 over 2 ohms. That is the total for these 2 up here. And this is also the same thing as having 1.5 ohms. Then it is in series with this 2 ohm resistor. And so we'll have it that the external, so total external resistance equal to 2 ohms plus 1.5 ohms, and that is 3.5 ohms. That is the first part. B says we should calculate the current in the circuit. Now, to calculate the current in the circuit, we need to determine, we know that current equal to V over R, or EMF over what? All the R plus all the internal resistance. So for us to get that done, we need to find the total E. Now, these E are the electromotive forces of these cells, and these E's are connected in what? They are connected in series. Total EMF of these cells connected in series will be 2 volts times the 3 of them, making a total of 6 volts. Then we need to get the total internal resistance, the total internal resistance. And how do we get that? So we get that by multiplying each of the resistance by 3, because we have 3 internal resistors. So we have 0.5 multiplied by 3, and that would give 1.5 ohms. So with that done, we have our current, which is what we are looking for, the current flowing in the circuit, equal to the total EMF, that is 6 volts, over R, that's 3.5, plus the small r, which is 1.5, and that would give 6 over 5. So the current flowing in the circuit will be equal to 1.2 ampere. That has been done. Move on to C. C says we should calculate the lost volts in the battery. Now there are two methods of finding the lost volts in the battery. Let's look at the first method. The first method is the lost volt is as a result of the internal resistor. And so to get the lost volts, we know that voltage equals to I times R. The R is internal resistance and I here is the current. So the volts is what we are looking for, the lost volts, and the current flowing in this circuit is 1.2. So 1.2 times the internal resistance, the total is 1.5. So when we multiply these two, that would give us 1.8 volts. And then I said there is another method which we can use. The other method to use is for us to find the potential difference across 2 points when it is not delivering any current. So to do that, we could find the potential difference across the circuit while it is not delivering any current, and we could say that, so this is a method 2. Here is method 1. So we get that by saying that we have that V equals to IR, and our I is still 1.2 and our R is 3.5. That is the total external resistance. That's 3.5. So when we multiply this, that gives us 4.2 volts. Now with this 4.2 volts, we have that the total voltage equals to 6 volts. So we have the total voltage, which is 6 volts minus 4.2 volts, and that will give us 1.8 volts. So that's how we could get the lost voltage. And then the last part of the question says that we should calculate the current in one of the 3 ohm resistor. Now in this 3 ohm resistor, we are asked to calculate the current that is flowing through it. Now we know that the current flowing in the circuit is 1.2 ampere, but whenever the current flows into this place where it diverges, there will be a kind of sharing in the current that will come here and come here based on the resistor that we have here. So what we should take note first is that the potential difference across these points is the same thing. So with the potential difference, you can easily get the current. So the first thing we should take note of is that, so we are saying the potential difference across the 3 ohms are the same. So we have that the potential difference across it equals to the current times R. So the current flowing at this point will be 1.2 times the total R of this, which is 3/2. When we multiply this out, we have 1.8 volts. Now this particular potential difference is what we are going to apply to each of the resistors. To now get the currents that is flowing in each of them, we have it that current equal to V/R, and here our voltage is what, 1.8, and the resistance is 3. So we have 1.8 divided by 3, and that gives us 0.6 ampere. This is the current that flows here, and this is the current that also flows here. 0.6 is the current. Alright, so here comes the next question, which says 3 4-ohm resistors connected in parallel have a potential difference of 16 volts applied across them. What is the total current in the circuit? For us to solve this, we're told that there are 3 4-ohm resistors which are in parallel, and then we have a potential difference that's applied across the resistors. We have to find the current flowing in the circuit. So to get this done, what we need to do is to first calculate the total resistance. So we have the total resistance to be 1/4, 1/4, and 1/4. So we have 3/4 when we find the LCM of all this. So our total resistance for the parallel resistors is 4/3. Next is to find the current which is flowing through it. Now we have that current equal to voltage over resistance. So our voltage in the question is 16. So we have 16 divided by R. Our R is the total resistance, that is 4/3. So we have that 16 multiplied by 3/4. So 4 cancels 16. We have 4. So 4 times 3 gives us 12 ampere as the current that is flowing through the circuit. So here comes the next question. It says that in the diagram above, the value of V1 and V2 are respectively what? So we have a cell of 2 volt EMF has an internal resistance of 1 ohm and 3 ohm external resistor and a 2 ohm external resistor. So in this question, we want to calculate the value of V1 and V2. That is the potential difference across the 2 external resistors. Now, for us to get that done, first we need to know the current that is flowing through this circuit. Now, when we get the current, we can apply a potential difference across this resistor and then apply a potential difference across this resistor. Alright, so let's get that done. So the first thing we'll do is to calculate the total resistance. Here, the total resistance, we have 3 ohms plus 2 ohms with this internal resistance, which is 1 ohm, and that gives us 6 ohms. So that is the total resistance. Next, we want to find the current flowing through the circuit. We have I equal to EMF over the total R, that's R plus R, that's the external plus the internal. Our EMF is 2 volts, and then the total R's are 6. So the current flowing through the circuit equal to what? 0.33 ampere. Now, with that current that is flowing through the circuit, we will now apply the potential difference across this. So we have V equal to IR. So we want to do that of the 3 ohm resistor now. So the voltage equal to the current, which is 0.3, multiplied by the resistance, which is 3 ohms, and that would give us 1 volt. Alright, so that's 1 volt that is flowing across the 3 ohm resistor. Then for the 2 ohm resistor, the current that will be flowing through it, we'll have it at V equal to IR. Our current is still 0.33 and our resistance is 2. When we multiply this, we would have 0.66 volts. So here we have the volt of 1 volt and then we have 0.66 volts here. So here's the next question, which says a cell whose internal resistance is 0.5 ohm delivers a current of 4 ampere to an external resistor. The loss voltage of the cell is what? So we can easily calculate the loss voltage because we're told that there's a current of 4.4 ampere and it has an internal resistance of 0.5 ohms. Now the loss voltage is simply I times R. That is the current flowing through the circuit times the internal resistance, and that is 4 times 0.5, and that gives 2 volts. So here is the value of the loss voltage. Alright, so this next question says if a metal wire 4 meter long and cross-sectional area 0.8 millimeter square has a resistance of 6 ohm, find the resistivity of the wire. Alright, so in this question we're told that the wire is 4 meter long. That's a cross-sectional area of 0.8 millimeter squared. It has a resistance of 6 ohms. The question asks us to find the resistivity. So we have a formula that says resistivity equal to resistance times cross-sectional area over the length. Now the first thing now is that in this question we're given our area in 0.8 millimeter squared while the length is in meter, so we need to convert this into an SI unit. And when you are converting 0.8 millimeter squared to meter, what you need to divide with 1 million. Why is it 1 million? Because milli is over 1000, but you have it in square, so 1000 squared gives 1 million, and so this will give us 8 times 10 raised power minus 7, right, meter squared. So substitute our values into this equation. R is 6 and then the cross-sectional area is 8 times 10 raised power minus 7, then L is 4, and so when we cut this we have 2 here, so we are left with 12 times 10 raised power minus 7 ohms meter. From the diagram, determine the value of the resistance X. So we have a circuit here where we have a resistance of 2 ohms and we have 3 ohms and an X in parallel, and then we have a 1.5 ohms outside here. So we want to calculate the value of this x. So what we could do first is to calculate what R will be using this volt and using this current. So we have that our R equal to voltage over current. Our voltage is 12 and our current is 2. So 12 divided by 2 gives us 6 ohms. So when we add all this, it will amount to 6. So let's get into doing that now. Now for this one, say that the total resistance equal to 2 plus all of this. Let's take all of this to be y plus 1.5. So that is the total. And then we have the total resistance to be what? 6. So that's 2 plus 1.5. That gives us 3.5 plus y. So y equal to 6 minus 3.5. And that leaves us with 2.5 ohms. When we add this parallel resistance, we will get 2.5. So let's get this 2.5 in fraction. That will be 2.5, and that is 5 over 2 ohms. So we now have it that 1 over RT equal to 1 over 3 plus 1 over x. Now our RT here is 5 over 2. So we have it that 1 over 5 over 2 equal to 1 over 3 plus 1 over x. So we have these two comes up as 2 over 5 equal to 1 over 3 plus 1 over x. Alright? We collect like terms where we have 2 over 5 minus 1 over 3 equal to 1 over x. We find the LCM of all this, and that is 15. That's 3 times 2, 6. 3 into 5 is 15. 3 into 15 is 5. 5 times 1 is 5. So 1 over x. So we have 1 over 15 equal to 1 over x. So 1 over 15, we said is equal to 1 over x. So when we cross multiply this, 1 multiplies x, 1 multiplies x, and 1 multiplies 15. So we have x equal to 15. So the value of x over here is 15 ohms. Alright, so this next question says the diagram above shows a balanced meter bridge. The value of x is what? So here is a meter bridge where we have two resistors in parallel, 8 ohms and 8 ohms, and we have another 8 ohms over here. Now we adjust this wire here such that it became balanced, and here is a galvanometer. So for us to find the value of x, we need to do a kind of ratio calculation. So what we'll do first is to find the total resistance in this parallel resistor. So we have 1 over RT equal to 1 over 8 plus 1 over 8. So we have 2 over 8, and that gives us 1 over 4. Hence our RT equal to what? 4. So we have it that 4 for this one over 8 here equal to x over 100 minus x. So this is how we apply the formula. So this cross multiply, 100 multiplies 100 minus x, we have this, and 8 multiplies x, we have 8x. So this is 400 minus 4x equal to 8x. We collect like terms, and we have 8x plus 4x, and that gives 12x. So x equal to 400 over 12. Hence the value of x is 33.33 centimeter. So that's the value of x. And to get this other side, we have 100 minus 33.33. It says a wire of 5 ohms resistance is drawn out so that its new length is 2 times the original length. If the resistivity of the wire remains the same and the cross-sectional area is halved, the new resistance is what? It says a wire of 5 ohms resistance is drawn out so that its new length is 2 times the original length. If the resistivity of the wire remains the same and the cross-sectional area is halved, the new resistance is what? Let's have our parameters. We're told that a wire has a resistance of 5 ohms. We have the original and then the new. So the resistance initially was 5 ohms. It was drawn out, and then its new length is 2 times the original length. So let's say that the new length was 1, meaning that the new length is now 2 times the original. Then if the resistivity of the wire remains the same, so when we say resistivity is the same, it's more like not putting it because it is the same, and the cross-sectional area is halved. So we have our cross-sectional area initially, let's say that it was 1, but in the new one it became halved, so half of the first one. We have to calculate the new resistance, so we are looking for the new resistance over here. So we apply our formula. Alright, so we have our formula which says that R equal to resistivity times length over the cross-sectional area. So we are going to apply it on the two sides. So we have heat here as well. Our R here is 5 and we have a resistivity which is constant and L is 1. Then area is 1. And over here we have our resistance to be unknown, which is what we do not know. We have our resistivity and our length as 2 and area as 1 over 2. So what we'll do here is we want P to be the subject of formula here and over here, and then we'll equate them. So we have 5 equal to P in the first instance, and in the second instance we have R equal to, we have resistivity 2 over times 2. Now this 2 over here comes up, so we have resistance equal to 4P equals to 4 resistivity, right? So we are going to equate, okay, make rho the subject of formula here. That will be rho equal to what? R over 4. Since the rho are the same, that is, they are constant, we can equate them and say, since rho equals to rho, so rho here is 5, and the resistivity here is 5, and the resistivity over here is R over 4. So we have R over 4. So what is the value of our R? R equal to 5 multiplied by 4, and that is what? 20 ohms.